Hello everyone, welcome back to this course on discrete mathematics, and now we are here in this new section called functions. And like previous sections, here again we are going to have three parts. So today we are going to see the introduction to functions, and later on we will see various aspects of functions including the inverse functions as well as the property of composition in a function. Let's begin by stating what is a function. A function takes an element from a set and maps it to a unique element in another set. Just now you studied about sets in the previous lecture, so you know what a set means. So function is little bit different when compared to that of set, but the transition from the set to the function would be quite easy, I suppose. Let's say, if we talk pictorially about a function, let's say we have, say, set x and you have a set y. A function is something that maps the elements in set x to the elements in set y. Let's say, for example, you have the element, say, x1, x2, x3, x4, and they are mapped to this elements in y. For example, you can consider this as y1, y2, y3, y4. And this mapping can be like, say, for example, right. So one of the properties of function is that every element of x has an arrow coming out of it. So that is one of the property, like every elements of x. We have x function as well as y. We have x set as well as y set. If this has to be a function while mapping, then every element of x should have one arrow coming out of it. That is one of the primary requirement. And there is another one, no element of x has two arrows coming out of it that point to two different elements of y, because that would be quite confusing and the mapping is not that perfect or proper. So those are the two important requirements of a function. The first one is every element of x should have an arrow coming out of it. The second one is no element of x has two arrows coming out of it. So no elements of x has two arrows coming out of it that points to two different elements of y. That is your actual statements that we have for functions. So as we move on, we will consider more about functions. For example, you can consider, like, if you have again x and y, and if suppose you have a function here, again you have x1, x2, say x3, y1, y2, y3. It is okay if two elements of the same set x is pointing to one element of y. It is still be fine, but there should not be two arrows coming out of the same element of the set x. We will consider that, and I will show you some examples to show what are the functions and what are not a functions. Let's move on. Here it is, an example. We have, say, for example, R real numbers and Z as the integers. So you have a set of real numbers, set of integers over here, and you are trying to map these elements. So that's your function terminology is building up. So you have a real number 4.3 and you are trying to map it with an integer 4. So f of x or f of 4.3 is implying to give us a result of 4. So we call this section of set on the left hand side that is going to be mapped on the right hand side is called the domain, and the element that is being mapped is called codomain. So these are some of the terminologies that you have to understand as we progress through this lecture. Moreover, this part, the 4.3 that is here, and there is a real number in this set, is called the pre-image of 4, and 4 is called the image of 4.3. So that's how we term all these notions as we move forward in this functions. Let's see more on this elements. So we call this f maps R to Z. That's the function here. So here is more on the functions. For example, you have the names Alice, Bob, Chris, Dave, Emma, and their grades A, B, C, D, F. So you could see Alice is mapped to A, Chris is mapped to A as well, and Bob is mapped to C, Dave is mapped to F, Emma is mapped to D. And did you notice that B, nobody gets B, but this is still a valid function. So here again, just to get back to the point what we were discussing about domain and codomain, here these names of the students are the domain and the codomain is the grade. Well, again, you can think of if there is a contradiction, if Alice has 2 grades for the same subject, yes, there would be. So that's one of the reason you could say like it doesn't fit into your function. That's why we say there is no 2 arrow comes out of the domain from a particular element. Let's see more on this and examine further to define the function as well as things that are not a function. Here is another example. You could say the strings A, B, B, C, 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 D, D, E are mapped to 1, 2, 3, 4, 5 and so on. So you could say like that is kind of a mapping string length function. So A and E, they are of length 1, so they are mapped to 1. B is mapped to 2 as well as D, and C is mapped to 4 because of 4 C's. But 3 and 5 are still free. They are not mapped to any elements from that set of strings. Again, the pre-image of 1 is A, and image of A is 1. Some functions are given stated here, A, E, I, O, U. Again, we are trying to set a range of 1, 2, 3 for A, E, I, O, U. So it's mapped to that part. And here, this thing that we talked about earlier, you can't have 2 arrows going out of the same element from the function that you are mapping. So here D, from D there are 2 elements that goes out, 2 arrows goes out, 1 to 2 and 1 to 5. In this instance, we could say it is not a valid function. And again, all the elements of your set in the domain should be mapped to some element in the codomain. So here E is not mapped to any elements. It's okay to keep the elements on the codomain not to be mapped, but all the elements in the domain should be mapped. Remember those conditions that I told earlier? Yes, every element of X has an arrow coming out of it. So suppose if this is your function X, and if this is your function, if you have a set X and set Y and you're mapping it by means of functions, in that case you have to remember those conditions that I mentioned earlier. We do have a function arithmetics. Let f1 of x is 2x and f2 of x is x square. In fact, you can perform simple arithmetic like addition, subtractions, multiplications, and so on. Say f1 plus f2 equals f1 plus f2 of x, that equals f1 of x plus f2 of x. That's quite simple, like 2x plus x square. And if you are thinking of other arithmetic operations, well, you can consider this one, f1 times f2, that is f1 times f2 of x, f1 of x times f2 of x, that equals 2x times x square, and that's nothing but it's 2x cubed there. Well, with this in mind, now we have defined what is a function. Let's see what are the different types of functions that are available. One-to-one function. A function is one-to-one if each element in the codomain has a unique preimage, meaning no two values map to the same result. They have a unique preimage. Let's consider this, for example. Yeah, all the part of the codomain here. For example, in this case, 1, 2, 3, 4, 5, all those things, as well as A, E, I, O in this domain, all these things has a unique element that are mapped to. In other words, we could also say that if you consider this as X set and if this is Y set, you can map X to Y as one-to-one, so that for all values of X they are mapped to some element in Y, and they should not be the same element. Let's consider further with another example where it is not. Say, for example, in this case, A and it's not A, it's E and O, they are mapped to the element 2. That should not be the case. For example, to state it simply, you could say if you have the 2 set, say x1, x2, y1, y2, so you should have a unique mapping of x to y. That should be a unique mapping. So this is an one-to-one function. Whereas if suppose you have the two functions, say x1, x2, x3, y1, y2, y3, and suppose you have x1 pointing to y1, x2 pointing to y3, and x3 pointing to y3. If this is the case, then this is not one-to-one function. It is not a one-to-one function. So if you want to state it in terms of things that we have learned earlier, you could say that for all values of x is an element of x if f of x1 equals f of x2, then x1 equals x2. So this is for a one-to-one function. And rather, if you want to say for a not one-to-one function, you could say that for some value or some elements, for some elements x1 and x2 in x with f of x1 equals f of x2 and x1 is not equal to x2. So this is the condition for not a one-to-one function. Yes, so function in general, they are being done a lot of work by the mathematicians, not only mathematicians, even from the beginning a lot of people have worked on some logics to come up with these function relations. So it's been famously said that don't accept a statement just because it is printed, because like before 50 years, even before 50, like say for example if it is before 100 years, if we have a printed document or anything that is printed, seems to be more valid and seems to be more authenticated. Well, that is not the true, but it may not be true. It may be deceiving for us. So we should be careful while defining the function, because functions can be deceiving as well, which at times looks like a function, but in turn it's not a function, or in other words, it at times looks like a one-to-one function, which is not a one-to-one function. So let's prove and disprove, as well as let's see various pictorial representation to show what are functions, what are one-to-one function, what are onto functions, and what other properties of functions therein. Let's move on here. More on one-to-one. So a one-to-one function is, in other words, called injective. A function is injection if it is one-to-one. So there can be an unused element in codomain. That's one of the interesting features of one-to-one function. Here it is. As you can see here, AEIO has been mapped to unique elements in the codomain as 1, 2, 4, 5, but the element 3 in the codomain has not mapped back to any elements. In other words, number 3 is unused. Yes, that is possible for the injection one-to-one function. That's what we are talking about. A function is onto. This is another type of function. A function is onto if each element in codomain is an image of some preimage, meaning all elements in the right is mapped. That's what we have to think about. For example, here AEIOU, and on the right you have 1, 2, 3, 4. As you could see, all the codomain part has been mapped to some preimage of AEIOU. If you recall the image and preimage, yeah, you would get that point. So let's see further on this function. Did you notice that why this is not an onto function? Yes, you are right. Element 3 and 4 has no pre-image for it, or in other words they are not mapped. So that's the basic idea behind an onto function. So basically an onto function, we also define an onto as for all values of, for example, for all values of y is an element of y, in which case some elements of x such is an element of x such that f of x equals y. So that is the statement for onto function. Whereas a statement, if you want for an not onto function, let's define it this way: for some elements of y in y such that for all elements of x is an element of x, f of x is not equal to y, right. So this is how we simply define an onto function. Let's see further on this. An onto function is also called a surjective, and they have some more properties. Note that there can be multiple used elements in codomain. That's the property of an onto function. As you can see, element 2 has been used twice, one from I and one from O. Both I and O are mapped to 2. Let's see, we can find what is the following things, whether it is one-to function or an onto function or neither. What about this? What do you think? Right, it is an one-to-one function, not onto. All the elements A, B, C has a unique elements mapped to it. How about this one? Yes, it's an onto function, not one-to-one. It's not one-to-one, as you can see, because two elements A and D are mapped to the same element, that is 2, and you know why it is onto, because each element has some elements, each elements of the codomain has been mapped to some elements in the domain. How about this one? Yes, this is both one-to-one and onto. It's quite unique, right? Yes, every elements of domain and codomain has uniquely mapped, no elements is missing. That's why it is both one-to-one as well as onto. And this one, how about this? This is neither one-to-one nor onto. Can you think of why it is? Say for example, since number 4 is not mapped to any other elements in the domain, we can say that it is not an onto function. And say A and C, they are mapped to the same element, that is 2, that's why it is not an one-to-one function. How about this one? This is quite interesting. Yes, it's not a valid function, as we have defined the function in the first few slides, that every element of x has an arrow coming out of it, but no elements of x has 2 arrows coming out of it. Yes, it cannot have 2 or more. Bijunctions. Consider a function that is both one-to-one and onto. So such a function that is one-to-one correspondence or bijunction, and these kind of functions has some unique features. Later we will see about the so-called inverse function, and these kind of functions has a unique role in that part. A function such that image and pre-image are always equal. For example, f of x is 1 times x, f of x is x plus 0, and here the domain and codomain must be the same set, that's x. And here's an example of a inverse function. Well, we will talk more about the inverse function in the next part, but I just want to explain the basic definition of the inverse function. Let's say f of x equals 2 times x, and here you have the two sets or that is the real numbers. Let's say we are mapping these two parts, and when you map it backwards you call f inverse, or that is nothing but the inverse function. Then what you are going to have? Yes, f inverse would be 1 by x by 2, because f of x is 2 times x or 2x. When you map it backwards, or if you want to neutralize the effect of 2x, that's how you are going to have x by 2. Say for example here your x is 4.3. So what happens while you are mapping? That is 2 times x, that is it becomes 8.6, right? While you are mapping, or while you are replacing f of x with 4.3, that equals 2 times 4.3, and that's 8.6. And if you want to take an inverse of this function, what are you supposed to do? Well, you know the function inverse is x by 2. So as we go inverse for that one, f inverse of x, that is f inverse of 8.6 equals 8.6 by 2, that's 4.3. Got it? Yeah, that's looks simple. Let's examine further on this thought of inverse function in our next part of the functions. So I'm looking forward to see you there. Until then, have a nice time and looking forward to see you. Goodbye.